In an earlier video, I talked about the electric field being the negative change in electric potential with respect to r hat. In a calculus-based course, this becomes negative dv dr r hat. Now we can make this a little bit more generalized. This is a sort of a specific direction right here, but you know, life rarely happens in one direction. So I want to introduce a much more proper equation, or more generalized equation. This is known as the nabla. It is the upside down delta with a vector symbol over it, and this right here would be the gradient. So the electric field is the negative gradient of V. If you haven't dealt with gradients before, this is just bonus knowledge. So the nabla deals with partial derivatives. And so first let's write out the definition. So I hat del x plus j hat del y plus k hat del z. These dels are indicating that we're dealing with a partial derivative. Notice that I have nothing after it. Basically, you're used to seeing d something dx. I have nothing after it. This is known as a vector operator. If v is equal to xy, my electric field would be the negative nabla of v, which is negative nabla of xy, and in essence, negative of this I hat del x plus j hat del y plus k hat del z of xy. Now what I would do here is I would distribute. Order does matter. And so this would become, my electric field is equal to negative I hat del xy del x plus j del y of xy plus k hat del z of xy. So all I've done is just basically, that's what I'm taking the derivative of. So now the question is, how do you do partial derivatives? Now, if you've done normal derivatives, so if I have v, let's do a different letter just so it doesn't get too confusing here. So let's say that I have m is equal to xy, and I take the derivative of m with respect to x. Well, I have two variables here. So m dx is y times dx plus x times dy dx. Using the product rule, that's equal to 1, so this just becomes y plus x dy dx. That is the formal full derivative. Partial derivatives are mathematically much easier. So if I did a partial derivative of m with respect to x, that is not a 2, that is a del, that I assume that that is the only variable. Anything else, y is not considered, and that would just be y. Del m del y would be equal to x. So up here, since I'm taking a partial derivative with respect to x, I assume everything else is constant, and so this becomes negative I hat times y plus j hat times, well, since y is my variable, x is considered constant, so this just becomes x. And since z is my variable here, those are both considered constant, so plus k hat times 0. In other words, my electric field would be negative y I hat minus x j hat. That's my electric field if my electric potential can be described by the formula xy. Let's take a look at that if graphing that out. So I set up axes here, beautifully drawn, as you can would expect nothing less. This is my x and y axis. So if I have, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3. So if I'm dealing with a potential of equal to 1, so I have 1, 1, and then 2, 1/2, 3, 1/3, 4, 1/4. And then on this direction over here, I'd have 1/2, 2, 1/3, 3, 1/4, 4. In other words, I would have a line that looks a lot like that. This is V equal to 1. This is an equipotential line because everything along that point is the same as the same potential. If I did V is equal to 2, I'd have this point 2, 1, and we'll go for the effects here. So 2, 1, and 1, 2, 4, and 1/2, and then 1/2 and 4. And we'd have this other set of lines right here. This is V is equal to 2. And let's go for another one here. Let's do V equal to 4. So I'd have the point 2, 2, 4, 1, 1, 4. And I would have a line that this is V is equal to 4. So if I was looking at the electric field, I know that my electric field, which we just figured out, is negative y I hat minus x j hat. Again, assuming I hat's in the x direction and j hat's in the y direction. So if I'm at the point of 2, 2, well, my electric field is negative 2 I hat minus 2 j hat, so that would be pointing in basically that direction right there. If I'm at this point right here, which is 4, 1, if electric, so this is the point 4, 1. So my electric field would therefore be negative 1 I hat minus 4 j hat. So I am here, negative 1 I hat minus 4 j hat puts it more like that. Notice, and it's not perfectly drawn, but notice that these look kind of perpendicular. Matter of fact, they should be perpendicular. So the bigger that the x component is, the more that it gets turned that way. And this is always going to be true, that the electric field is perpendicular to the equipotential line. If I have a conducting surface here, the surface, if this is in electrostatic equilibrium, then the surface is equipotential. Equipotential being equal potential. And therefore, since the electric field is perpendicular to the equipotential line, the electric field is perpendicular to the surface at that point right there. This would be my electric field. Therefore, the electric field is perpendicular to the surface.